We will now discuss the molar entropies of the ideal gas. Entropy is an extensive quantity, S, let's say n S bar. S bar is the molar entropy, n is the number of moles. By the way, if you have n gas particles, we divide by n0. This is the Avogadro's number, Avogadro's. And this is n. And Avogadro's number is defined such that n0 times the mass of the carbon 12 atom is equal to 12 grams. And furthermore, n0 times the Boltzmann constant is the gas constant R. All right. So we have du delta Q minus delta W. du for the ideal gas we discussed, that's n CV dt. Delta Q in a reversible process is S dt. And the work is minus P dV. Sorry, TdS. ds is delta Q over T. So ds is equal to 1 over T and CV dt plus P dV. And this is n ds bar, and it's just the constant number of moles. That's equal to n CV dt over T plus P dV. So we divide by n. And PV is equal to nRT. Therefore, P is nRT over V, which we can also write as n RT over V over n. So this is CV dt over T. Instead of P, we write plus RT dV over n over V over n. And we are dividing by T, P over T, P over T. T is cancelled. So we integrated ds. So S TV, the molar, so the entropy of 1 mole of ideal gas is CV log T from here plus R log V over n plus a constant which I will write as S0 TV. I will write with TV because our molar entropy is depending on T and V, or V over n. Since V is also extensive, V over n is intensive. So S is extensive, n times S bar, and S bar must be an intensive quantity. All right, So let me write this important result here. S TV. I'm writing this is n S bar TV. That's equal to n CV log T plus n R log V over n plus n S0 TV. So this is the entropy constant. And for classical thermodynamics, it's just a constant. And if you are computing entropy differences, in most of the time, this will go away. You take the difference, it goes away. Except, let us stop and think for this form a bit more. I will just write here. You see, consider the parameters T and V. For example, you cannot take temperature down to 0 because Cv for monoatomic gas or diatomic gas or polyatomic gas is constant, 3 over 2R for monoatomic gas. But it cannot remain to be constant, because if S equals 0 at T equals 0 and ds is equal to dq over t, so c of t dt over t. And if you are integrating at t equals 0, there's a logarithmic singularity. So c of t has to go 0. This is constant. So this formula cannot be used for all temperatures. In fact, this is the low temperature, low density, and high temperature limit of quantum gases. Gas particles are quantum particles. They are atoms or molecules, diatomic molecules or polyatomic molecules. Although we don't see them, there are lots of atoms flying around here. So it is the low density, high temperature limit of the quantum system. So if you just what makes S0 TV with the entropy 0 at temperature is 0, this will depend on temperature. But S0 TV will depend on, for example, the Planck's constant, which is the quantum constant that tells you how important the quantum effects are. It will depend on that. It will depend on the mass of the gas or the molecular weight of the gas. It will depend on Avogadro's number. It will depend on the ground state spin of the system, G, etc. In fact, if you want to write, S will be nR log G e to the, I am now writing the exact formula, 5 over 2 times rho lambda cubed. We will not play with this one. This you can obtain, take any quantum gas, ideal gas, and look at the low density high temperature limit. It gives you that. So this is, we can call it, if S0 TV is defined with those constants, well, I'm say what these things are. Rho is n over v, that's the number density, number per unit volume. And lambda cubed, lambda is it tells you it's the thermal wavelength, how well you can localize the particle. So this says that n times the volume in which you can localize the particle, VFT, which is lambda cubed, this must be very much smaller than total volume. So this is what we mean by low density and high temperature limit. Lambda, if temperature is high, lambda is small, okay, rho lambda cubed. So this has a name. This is the Sackur tetrode. Sackur tetrode. In most applications, we don't need what these things are because they just cancel. Except, for example, they survive. There are a few cases that they survive. For example, in gaseous chemical reactions. We will not go into them, so we'll just leave it there and take this as a constant. I just wanted to emphasize that this ordinary constant in classical thermodynamics really has a quantum connection with H. Okay. So I am erasing all this. We will not dwell upon it, just to mention that this form is that form, and this is derived as the low density high temperature limit of the quantum gases, ideal gases, and we say no more about it. Okay. Another perhaps explanation of the low density is that the molecule has a size. Let's say in room temperature, the oxygen molecule, which is a diatomic molecule, has the size 2 angstroms. Angstrom is a small length, never mind. But on the average, in between collisions, it flies about more than 1,000 times its size. So it has this size and then flies freely 1,000 times, more than 1,000 times its size. So that's low density. All right, so this is the TV version. Now we use other versions. PV is equal to nRT, or V over N is equal to N is gone, RT over P. So we just put that thing in. Let me just write here now for the moment to get rid of these. So this will be equal to CV log T plus R log RT over P plus S0 TV. And, well, we open up the log. This is CV plus R log T minus R log P plus R log R plus S0 TV. CV plus R is just CP. For ideal gases, CP is equal to CV plus R. And this is just the entropy constant, but in the case when we use as variables T and P. So this is S0 T and P, which is S0 TV plus R log R. So I'm writing this here. Tp is equal to Cp log T minus R log P plus S0 Tp. I'm erasing. So we use TV, TP, the last one is PV. We have to eliminate T. So PV is equal to nRT. T equals P V over N and 1 over R. So we have S equals Cp log P plus Cp log V over N plus minus Cp log R minus R log P plus S0 Tp, which is equal to, this is Cp minus R. So Cp minus R is equal to Cv. That's right. It is Cv log P plus Cp log V over N this minus Cp log R plus S0 Tp, which we can write as, we can write directly to here, S PV over N is equal to S PV, that's equal to Cv Cp minus R Cv log P plus Cp log V over N plus S0 PV, where S0 bar PV is equal to minus Cp log R plus S0 Tp. So these constants are related to each other by addition or subtraction of other constants involving R and Cp and Cv. Okay. As I told you, we will use simply as a constant, but if you look at what makes this constant, it is basically, it must come from quantum physics. I am erasing this. So these are the three forms of the, if you wish, the Socrates-Tetrode equation, but we don't write the interior of this constant. So let's now multiply everything by n, and n, 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 n. Okay. These are the molar entropies.